Chapter 13. Now in this chapter we are going to study vector functions, and specifically we do calculus on vector functions. Chapter 13.1 is about vector fields, and here we introduce vectors and two operations called divergence and curl. Okay, so before we discuss about vector fields, let's consider a cone field. A cone field is a field of cones. Similarly, a vector field is a field of vectors. Now, at every point, we have a vector that points in a specific direction with a specific magnitude. Fortunately, in Calculus 3, we study vectors in two-dimensional and three-dimensional spaces. Okay. Here is the general way we represent a vector field in 2D. So we have this vector field F, and vector field F has two components. The first component is F1 and second component is F2. Now in general, these two functions are functions of x and y. Basically your domain is in 2D, and we call these functions as the component functions. Here is an example for a two-dimensional vector field. Your vector field F equals to xi minus yj. Or sometimes we write the same vector field like this using this dot parentheses. So your first component is x, your second component is negative y. Let's evaluate this vector field at three different points: 2, 0, 0, 3 and 2, 4. So at 2, 0, our vector field becomes, so my vector field F equals to, okay, x component is 2, so you have 2, comma, y component is 0, so you have negative 0. So basically this is 2, 0. This means at 2, 0 you have a vector 2, 0. Second point, 0, 3. X component is 0, y component is 3. So your vector field is negative. So here you have negative y. So we should take the negative of the y component, which is negative 3. Similarly, we can find the vector at point 2, 4. X component is 2. So my vector function is, the first component of the vector function is the x coordinate, which is 2. The second component of the vector function equals to negative of the y coordinate. So it should be negative 4. Now, if you plot these vectors on the xy plane, you should get something like this. So here we have the xy plane. This is the x-axis. This is the y-axis. Okay, at 2, 0. At 2, 0. So this is 1, 2. At 2, 0, we have a vector. And my vector is also 2, 0. So basically the first component of the vector is 2. And the second component of the vector is 0. So our vector points in the positive x direction. At 0, 3. So this is the point 0, 3. My vector is 0, negative 3. So the x component is 0, but y component equals to negative 3. Since we have a negative number, our vector points towards the origin. something like this. Okay, and then at 2 comma 4, it's at 2 comma 4, maybe it's over here, your x component is 2, so x component is 2, y component is negative 4, therefore the resultant vector should point in a direction like this. Again, this is the point 2 comma 4, this is the point 2 comma 0, and here we have the point 0 comma 3. Okay. Now using Mathematica we can plot this vector field, and you should get something like this. So this is the diagram for the vector field that equals to x comma negative y. Okay. Now if we consider a vector field in three-dimensional space, it should have three components, f1, f2 and f3. Now these components functions are functions of x, y and z. So at each point in three-dimensional space we have a vector. As an example, let's say maybe this is a, let's say xy, the first component is xy, second component is cosine of yc, third component is c squared. This is an example for a vector field in three-dimensional space. Now it is very difficult to plot a vector field in three-dimensional space using hand. So here I plot, using Mathematica I plot a three-dimensional vector space, and this vector space is given by the function f of x comma y comma c equals to, first component is x squared yc, second component is minus yc, and third component is e to the c. The example. So this is an example for a vector field in three-dimensional space. So as you can see, at every point in R3 we have a vector that points in a specific direction with a specific magnitude.